Good morning. Today we're going to talk about start the module on sequences. So hopefully you guys printed out this note sheet for today. Alright, so we're looking at trying to find the next term in each of these patterns. Again, any number pattern is called a sequence. So we have, starting with 1, goes to 1/2, 1/3, 1/4, 1/5. I guess what the next term in the sequence is. That's right, Ben. It's 1/6. Good job. Next sequence: 2, -4, 6, -8, 10. What is the next number in that sequence? That is correct, Alex. It is -12. Alright, so here's our number sequences. So sometimes it says here it's easy to represent a sequence with a function. And we could do so by graphing it. So let's go ahead and graph this first one. So you notice that our terms here for this first pattern starts at 1 and then steadily decreases as we move on to the second term, third term, fourth term, and so on. Okay, so on the x-axis we are going to have numbers that represent the term, the term number, let's do that. Term number and the actual term value will go along the y-axis. Okay? So we'll start with the first term. So that first term has a term value of 1. Okay, so then we move on to the second term. Second term is a value of 1/2. So let's try to make this appropriately spaced. So there's 1/2. So I got one term at 1. Second term is at 1/2. Third term is at 1/3. Right around here. Fourth term at 1/4. Okay, so we see, again, for this particular sequence, right, here's our graph, curving, right, as our term numbers go along. Right. Move on to the next thing here. So it says a sequence is usually represented by listing several of its terms in order. Right, so we typically number the terms using subscripts. So if we want to have a variable represent the first term, it's going to be a sub 1. Right? So a sub 1 represents the first term of the sequence, followed by a sub 2, the second term, a sub 3 is the third term, a sub 4 is the fourth term, and so on. And this can go on until we get to a sub n, which represents the nth term. Okay, so depending on how many terms there are in the sequence, okay, so n is going to represent how far we go in that sequence. When we can find a formula for the nth term in the sequence, sometimes called a progression, we can represent the entire sequence with that formula. So let's move on to example 1. It says find the first 5 terms of this sequence. So I need everybody to write down the sequence. So S sub n is going to represent the sequence, and that sequence is going to be determined by this formula, n squared times n plus 1. Alright, so I'm going to give you here some time to try to find the first 5 terms of the sequence, where again n represents the term number. So if you want to find the first term, so the a sub 1 term, to do that we're going to plug 1 in for n. 1 squared times 1 plus 1. So the first term is going to have a value of 2. Find the second term. According to this formula, again, n represents the term number, so all we got to do is plug in 2 in for n. So we got 2 squared times 2 plus 1, and that's going to equal 12. Find the third term, 3 in for n, to the formula, again, n is equal to, the third term is 36, 4 squared, 4 plus 1 equals 80. And the fifth term, we've got 5 in for n. Do the math, and we get 150. Okay, so this is how you use the formula, right, for a sequence. And with n representing the term number, all you have to do is plug in that term number into the formula and find that value. Alright, so I will give you now a couple minutes to see if you can figure out the first 5 terms of this sequence defined by this formula. Alright, guys, that did that pretty well. So, you're right, got a first term is 1/2. Second term is negative 4/3. Third term, when you plug in 3 in for n, okay, plug 3 in for n, you should get 9/4. 4 in for n for the fourth term, negative 16/5. And for that fifth term, again, you're plugging 5 in for n. You're plugging 5 in for n, you get 25/6. Okay. Alright, so let's go ahead and go on to the second page of the notes. It says, can you write the nth term of each of the following sequences suggested by the pattern? Okay, so we're trying to write that generic nth term. Okay, so again, technically these patterns, these sequences can go on forever if we allow it to. Alright, so we want to write that expression represents, right, basically what the pattern is. So we got 2/3, 4/9, 8/12, 16/81. So we're trying to look for something that's common between these terms. Trying to figure out, okay, what is the pattern? How are these numbers changing? So often you would like to kind of see if you can find a common factor. Like how do we get from one term to the next? And if you look closely, you're going to notice that, right, in the numerator, it's increasing by a factor of 2. So you get 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and so on. So we know that, right, as we move along this pattern, right, we can predict the next one here would be like 32. for the numerator, and look at the denominator, you go from 3 to 9, 27 to 81, you see, okay, yeah, these, you get from one number to the next, from one term to the next, you're multiplying by 3. So, figure that 2 over 3 is going to be part of that nth term, some factor of 2 and some factor of 3. So, I want to see, okay, so since it's being multiplied, so repetitive multiplication we know is being shown when we use exponents. So, if we do this, we're going to see that 2 to the n over 3 to the n is the way we can describe that nth term. So and we can test this out too, right? So if we plug 1 in for n for the first term, if I plug 1 in for n, I get 2 to the first over 3 to the first, which is 2/3. If I plug 2 in for n, then 2 representing the second term, I get 2 squared, which is 4, over 3 squared, which is 9. Okay, just one more to test it. 3 represents the third term, so when I plug in 3 in for n, I get 2 to the third power, which is 8, over 3 to the third power, which is 27. Okay, so that is the pattern. Right, so here we have an expression that we can represent the nth term, or we can write this in another way, 2/3 to the nth power. Now the next two examples are examples of what's called an alternating sequence. So you notice here it goes from a positive 2 to a negative 4 to a positive 6, negative 8, positive 10. So we see that the signs, right, positive and negative, they are alternating in this sequence. Okay, so anytime you see an alternating sign sequence like this, know that when you're trying to write an expression or formula that represents the sequence or the nth term, that there's always going to be a factor of -1 involved. Okay. Because you know that in order to change a positive to a negative, you've got to multiply by -1. Right? But because it's alternating from positive to negative, right, we want to be able to, hey, if we wanted to change that negative value to a positive value, and the way we can do that is by attaching an exponent. So for this one, we're going to attach an exponent of n plus 1. Alright, so you can see, just kind of testing this out. Right. Again, our first term is a positive number. So if 1, we plug 1 in for n, I get 1 plus 1 is 2. And -1 to the second power, right, -1 to an even power makes it now positive. Okay, so we're going to have our positive sign there. If I plug 2 in for n, again 2 representing my second term, here my second term is negative. If I plug 2 in for n, I get 2 plus 1 is 3 for my exponent. That exponent is odd, and then anytime we take a negative number to an odd power, that's going to leave us with a negative value. Okay, so you see here this expression is going to allow us to alternate between a net positive and a negative value term. Right? Plug 3 in for n, again 3 representing the third term. Right, so 3 plus 1 is 4. -1 to that even power is going to give me an even, it's going to give me a positive value. Okay. Alright, so we're going to stop here today. I'm going to pick this back up in tomorrow's video. I hope you guys have a good day. See you tomorrow.